আমাদের আজকে স্পিকার হচ্ছে ডক্টর নাদিম চৌধুরী ও অ্যাসিস্ট্যান্ট প্রফেসর বুয়েট ত্রিপুরী। সো নাদিমকে নিয়ে আসলে খুব বেশি কিছু বলার নাই। নাদিম ডিভাইস ফিল্ডে ও রিমার্কেবল কাজ করেছে MIT-তে থাকতে ও এখনো করে যাচ্ছে। He has many publications in top journals of IEEE. তারপরে হচ্ছে more than 10 patents আছে। সো এগুলো তোমরা হয়তো বায়োগ্রাফিতে অলরেডি পড়েছো। যেটা নাই সেটা হচ্ছে যে রিসেন্টলি ওর একটা কাজ IBM অ্যাকসেপ্টেড হয়েছে, সেটা হচ্ছে আমাদের যারা আমরা ডিভাইস ফিল্ডে কাজ করি খুবই প্রেস্টিজিয়াস একটা কনফারেন্স, ইন্টারন্যাশনাল ইলেকট্রন ডিভাইসেস মিটিং। আমার ধারণা যে বাংলাদেশ থেকে মোস্ট লাইকলি দিস ইজ দ্য ফার্স্ট টাইম যে আমরা IDM কনফারেন্সে বাংলাদেশ থেকে কেউ যাচ্ছে। সো দিস ইজ ভেরি প্রেস্টিজিয়াস। সো আমি আসলে কথা বলাচ্ছি না, থ্যাংক ইউ সবাইকে আসার জন্য। আমাদের আরও কিছু স্টুডেন্টস আর ফ্যাকাল্টিসরা হয়তো জয়েন করবে, আমরা টাইমলি শুরু করতে চাই। সো ওভার টু ইউ নাদিম।
Thank you very much for the kind introduction. So today I'm going to talk about mostly like the works that I'm going to present today. It has been done while I was doing my PhD. At the later part of my presentation, I will talk briefly about the works that I'm doing currently with my group. So today the title of the talk is gallium nitride based complementary electronics. So we all know what is a complementary electronics. Basically you have a N-type transistor which normally works as a pull down network, and you have a P-type transistor which works as a pull up network. And you use this configuration as a switch. That's basically an inverter, right? So what it does, it basically reduces the power that you need to switch from high to low, because you're only consuming power when the switching is happening. In the static state, the power is almost zero, and that's what we call complementary electrons. So unfortunately for GAN, when I started my PhD, there was no complementary electrons. So it was all based on N-type transistor. So basically what you have a pull down network which is based on an N-type transistor, and the pull up network is basically a resistor. So since it is a resistor, so it's always conducting current, you have IS current loss. So the power loss is much higher. So during my PhD, we started developing this complementary platform. The project was funded by Intel, and later on it was funded by IEEE. So the first thing is that why do we even need a GAN complementary electrons? We already have a silicon CMOS, and we are happy with that. Like all the AI revolution that is happening because of the silicon CMOS that we have in all of our cell phones, even in the projector as well, in the laptop as well. So let's look at the things that we can relate to. For example, we all know that there is currently a revolution going on. I would say it's an electrification revolution. Why? Because think about the most mechanical device that you can think of. It's a car, right? The car that we drive is basically a mechanical device. And right now it is being electrified. So basically right now we're talking about EV. It's fully electric vehicle. So the most mechanical device is actually being electrified. And when we talk about intelligence, it's a biological thing, right? Intelligence, so we are intelligent. Every living being it has some intelligence, but normally machines they really don't have intelligence in that sense. But when we use ChatGPT, it has some intelligence, right? You can have like meaningful conversation with ChatGPT. So why even the intelligence is actually being electrified? But so I will here just show the AI as a test case, but we can apply the same idea to different fields as well. So So for AI, for example, you need a huge amount of data, right? And you also need a huge or relatively larger neural network. We call it large language models or something like that. So basically what it means is that you have a neural network which have like billions of parameters. Right now it's actually in trillions. And you need to put all of these things, data and the neural network, into data center. And you have to train them for hours, months, maybe years. And for that we need power. How much power you need? Let's look at this statistic. This is a relatively older statistic because this is from 2022. So very interesting thing. So right now Bangladesh, the power consumption per year is about 80 terawatt hour right now. So look at the data center power consumption. It's around 200 to 250. So data center alone is consuming more power than countries, for example, South Africa, Egypt, Argentina, Bangladesh. So it's consuming more and more power. Now, Google, Microsoft, they are thinking of setting up nuclear power plant to supply power to the data centers. So here, I'm just giving you an example. For example, ChatGPT 4, it has 1.76 trillion parameters. And they are trying to make it more intelligent. More intelligence means more parameters. More parameter means more energy is required to train, and it actually goes by square. So you need, in future, you actually need more and more power to train these models. It's actually not just the training. When we are using those models in ChatGPT or in other form, that also requires power. So everything we are talking about intelligence, it's basically nothing but the energy. Okay, so now let's look at the why are we talking about power? Because ultimately the power goes from your, the power lines or the wall adapter to wall socket to the rack. So normally rack voltage is around 48 volt. So the rack, that is the rack voltage. So if you input 48 DC, your processor runs at right now 0.6, 0.7 volt. So 48 to 0.7 you have to do a DC-DC conversion. And then from AC to DC, you have to go from 3-phase AC to 48 volt. That is also power conversion. So all of this conversion actually is not that energy efficient. Right now it's around 75% efficient. That means you are losing 25% of the power there. So 25% of the power are never there in the processor. But we can change that. We can actually make it more energy efficient, and actually right now we have some work with Chancellor to show that it can be possible to make these converters up to 98% efficient. So there is a huge room for opportunity there. And we're talking about in the range of trillion watts of power. Okay, so it's actually not just the power for the processor. If you think about it, the 25% that are being lost, those are lost in what form? Those are lost as thermal energy. So you are actually making the data centers more and more like hotter, right? As you're using the data center. So you have to cool them down because you know that silicon chips, they cannot operate beyond 160 degrees Celsius, like safe operating in 160. So you have to cool them down. So in general, in a typical data center, you actually use 43% of the total energy in cooling the data center. So when you have very high efficiency in the range of 95-96%, that means you're only losing 4% of the power as heat. So you're not generating that much heat. So you don't need that much cooling as well. So you have energy savings there. Another most important thing, this is an NVIDIA board. So you look at the chip at the center. This is the chip that NVIDIA makes, right? This is the chip. What all of these things are doing? These are all power converters. So you have like at the center of the chip, you need to supply the power, right? And you need all these power converters, inductors, capacitors. So in terms of the volume, if you look at the volume of these systems, about 60 to 80% of the volume is basically for power electronics. Right? So when you use technology like gallium nitride, you actually can make the system smaller. Why? So this is a very fundamental thing. So the way DC-DC converter works is basically you put the energy in the inductor and the capacitor. So as you know, if you have to put more energy, the inductor and capacitor size has to be big. But think about it. So basically what you're doing in a power conversion, you're putting the energy into the capacitor, and then in the next cycle you're taking it out. Putting energy, taking it out. So think about it. If you need to put less amount of energy, then you can reduce the size of the inductor or capacitor. And for that, you need to do this at a faster rate. That means your switching frequency has to increase. Normally, if you use silicon transistor, you cannot switch in the range of megahertz. At best, 100 kilo or something. So by increasing the switching frequency of the power circuits or transistors, you can actually reduce the solution size significantly. This is just an example of TI system, the 4x reduction. Theoretically, it could be 10x, even more than that. So basically, so basically, you increase the switch efficiency, you reduce the size, and overall you reduce the cost. Why cost reduction? Because you don't need cooling power. You can, if you reduce the size, you can put more and more of these chips in a given data center. So your computational capability also increases. So the overall cost of computation goes down. Okay, so now let's talk about why are we even thinking about GaN or silicon. It's basically, it is an amazing material. Like all of these, like I can see, this is an LED, right? So right now the lighting, the whole lighting industry is about $30 billion industry. It's all GaN, right? And the whole gallium nitride electrons start from there. So it's an amazing material. So not only for silicon transistor, the way you introduce charge in the channel by inversion, here you can do that because it has spontaneous polarization. You can use that to design the layer such that you have very high charge density in the channel. It has very high electron mobility and as well as the saturation velocity. That means if you can make the devices, it will be much faster than the silicon. And because of all of these amazing properties, if you make a transistor called 𝐓𝐢𝐭𝐥𝐞, it has very high electron current density, low on resistance, and higher switching frequency. R1 times Q switching frequency. Basically, switching frequency, if you have very high switching frequency minute, that means, sorry, very low switching frequency minute, that means you can actually switch it at high frequency as well as carry more current. And because of that, right now actually you can buy, this is not like theoretical work, and this is like, you can literally buy gallium nitride transistors from the market. So this is a 65 or 67 watt angle charger, right? Normally, if you want to have 65 watt charger in the silicon, it will look like this. It will really. And this is, they call it, the model is from Anker's GaN Nano. It has a GaN transistor and switching at much higher frequency, close to a megahertz. That's why they can reduce the size down to this. Think about if you can switch it at 10 megahertz, it could be even smaller. So this is like, I mean, I've been using it for like 2 years now. So things work. That's why the whole market is there. Okay, so Why do we need an integrated platform? Because without the integration, you really cannot increase the the complexity of the circuit. So, for example, in a power electronics circuit, you need a lot of sensing. You have to sense the current for the overdrive. You have to sense the temperature. So, for all of this sensing, and then you have to make a decision. So, sensing and decision making, you need logic. Right? Without logic, you cannot do it. And for logic, you need a complementary network. So, you need a pull-up network and a pull-down network. So it's not like there is no platform right now. So right now there are few platforms that are available. So for the pull-down network, they only use intern, which is what everyone should use. But for the pull-up network, I make EPFM. They use different technology, basically intern transistor or a resistor. So for the pull-up network, either you use a keynote transistor that is already always on. So when the transistor is always on, it's basically a resistor, right? Or you use a real resistor. Intel actually has a lot of applications on this. So what they try to get the best of both worlds. So they have the silicon N-type GaN transistor, and they have silicon P transistor, and then they do the heterogeneous 3D heterogeneous integration. Because for a given geometry, N-type GaN transistor is 100 times better than the silicon transistor. So they get the N-type from GaN and P-type from silicon germanium, and then they combine it in a 3D representation. But it's costly. Whenever you do this 3D integration, it's not cheap. So to make the whole thing, commercially feasible, we really need a P-type transistor, GaN P-type transistor. So before my PhD, there has been a very few works on GaN P-type transistor, but look at here. So this is the on-off ratio, and this is the current density, milliampere per millimeter. So typically for an N-type GaN transistor, the current density is around 1000 milliampere per millimeter. But look at all the numbers for the P-type. It's like almost 2 orders of magnitude more. So, and they also have some other issues of these demonstrations. So why is it so difficult to make a P-type GaN transistor? So the first difficulty is that it's very difficult to have holes. It's easier to have electrons in a GaN system, but very difficult to generate holes in gallium nitride. Why? Because as you know, when you try to dope, for example, to make an N-type silicon, what do? You dope with phosphorus. What is the activation energy? 35 millielectron. So what is the room temperature energy? 25 millielectron. So at room temperature, most of the dopants are activated because the activation energy is much lower, very close to the room temperature, right? But in gallium nitride, it's around 200 millielectron. So at room temperature, only a fraction of the dopants are activated. Actually, it's around 1 to 2%. So basically, if you dope gallium nitride material with magnesium in the range of 10 to the power 18, you will end up having holes in the range of 10 to the power 60. Because you don't, only 1% is activated. So that's a big problem. Okay? So that's number one. Second is the hole mode. So again, it's a wide band material. So, right, it's normally hole mobility is lower than electron mobility, that you know, right? Why is that? It's coming from the band structure. So normally, if a material is wide band gap, the band structure is such that the mobility is always going to be low, especially the hole mobility, because this band structure is kind of like flat. And there is actually no way to improve that. Maybe we can apply some strain, but those kind of works are going on right now. So that's number two. Normally for electrons, the mobility is in the range of thousands, 2000 maybe. And for holes, it's in the range of maybe less than 100. And then the high contact resistance. Because you don't have that many holes, when you try to make a metal semiconductor contact, it's going to be very resistive. So high contact resistance. That's also So we're going to solve all of these problems. Let's see. So how we're going to do that? So we're not going to dope the material. We're going to use the polarization charge to make the holes. So we do some band engineering and try to have the whole gas instead of doping the semiconductor. That's one. Mobility. So mobility is basically, how do you put it, right? So basically, if you have to, if your home is in mid-Pune, if you have to travel every day to Dhaka University, and if you commute by rickshaw, it's going to take a long time. Only way to solve that is if you move to hall, and then the mobility doesn't matter. So you basically scale the device so that the holes don't need to travel longer distance. So that's number 2. And for the high contact resistance, basically, it's very difficult to get high work function metals, but there are some metals, if you oxidize them, the work function kind of like becomes around 6 something electron. So one of them is actually nickel oxide. So we'll try that. So these are the 3 different ways we're going to improve the device problem. So this is all motivation and background. Now let's talk about the outline of this presentation. So don't worry, so I will go through them very quickly. I will not focus too much on the technical details, but I will try to give you an overview. So first, I'm going to talk about the complementary platform that we're going to present today. And then we have developed 3 different generations of devices. We'll talk about that briefly. And then some of the process technologies that we have developed later on. And then I will summarize my technical talk. And then I will give you a brief introduction of my group at BUET, what we're doing. Okay. So basically, if you want to have N-type and P-type transistor, you need electrons and holes in the same wafer. Okay. So the way to do is basically you grow. These are all on silicon valley. So you grow GaN buffer to have the lattice. The purpose of the buffer is to manage the stress between the silicon and GaN because they have different lattices. And then you grow L-GaN on top of GaN. And because of the polarization charge difference, they have electron gas advantages. And then you grow another GaN layer. And because of the polarization charge difference, they have to be whole gas. And then to connect to this whole gas, you grow P-GaN and P++. P++ is for the contact. And this is the epi that we have designed. And we did a lot of TCAD simulation to optimize this structure. After all of the optimization, we sent out the design to a company called Finwave Semiconductor, basically a Chinese company. The founder, I knew him very well, Chancellor. His company is valued now $1 billion. But when he started working with us, so this is a GaN on silicon wafer. One of the wafers that is basically the same wafer. So it kind of looks like a mirror. 150 millimeter wafer, 6-inch wafer. So we give them the design, they build the wafer and ship it to us. And then we start processing that input. So before processing, what I do is that take the wafer, dice it, and make it 1.5 centimeter by 1.5 centimeter piece. And then we process those pieces. Because these wafers are very expensive. So even though MK Semiconductor were giving them for free, because in our paper we write them their name because they were a startup, so that will be kind of like the marketing, and then we'll get a free. So I got about 40 wafers during my whole PhD. So each wafer is like $5,000 US, which is very expensive. Okay, so this is a like 6-inch wafer, and we need to make sure before we process that it really has the L-GaN GaN. You can see that at the top you have this GaN and GaN interface. So you have this two interface here. Okay, so we have the wafer, and then we start doing the process. First, we did the mesa etching, and then we do selective etching, kind of like etch away the P++ P-GaN layer. I'm not going to the details of the process. I think I'm not sure whether do you have fabrication classes here? Some of you can understand. So basically, the bottom line is that we make an inverter. Okay. So after all of these processes, we have an N-type device, emote. We have a P-type device, keynote, and then you connect them at the gate to make an inverter. So even though I'm saying this, just to let you know that for my first transistor to work, I had to work like a year. So we designed the AP, send it to Kai. They would send us the wafer. I did the processing, nothing works. So I do after 1 month of processing, I tried to do the measurement and see that it's a resistor. Basically, there is no gate voltage. So you apply bias at the gate, but you don't see any change in the current. So it has been going on for months. Okay? Finally, one fine morning, I got what I wanted. So basically, you have the N-type transistor, P-type transistor, and you can see that this is a P-type transistor, this is N-type. You see the width. N-type width is much smaller than the P-type. Why? Because for an inverter to work, you have to match the current. So the current density in the P-type is much lower. That's why you have to make the width wider to match the current. And here is the input-output waveform. So you can see the inversion. So basically, when your input is low, inverter output should be high. So input output. And we tested this inverter up to 300 degrees Celsius and it works, even at 300 degrees Celsius. I made all the gates, all the logic gates that you need, like NAND, NOR, SRAM. But I'm not going to that. So, but we had some problem. You see, like one of the major problems is that if you look at the switchings. So if you look at the switchings, fall time, so rise time is much higher than fall time. You see, that is not what you want because that is going to limit your switching speed. So why is that? So if you look at the current density, if you put both N-type and P-type in the same scale, you cannot even see the currents in the P-type. You put it in the same scale. But if you can see it has current, but it's very low. Current density is very low. So that's why we need to make the gate device wider. So we need to improve the current density. Okay? So that's the learning from generation 1. So now let's take this learning to generation 2. So what we have done is that we have analyzed what are the sources of resistance in this device. So we have the contact resistance, which is in the red, and then we have the excess resistance, and then we have the channel resistance. So contact and channel we cannot get rid of, but excess we can. So if we make a self-aligned device, we can get rid of the excess resistance and try to improve the current density. Then we did the processing again, and this is a device. I think I presented this to IEEE 2019. So this at that time it was the smallest P-type device. It has channel length of about 100 nanometer. And we could improve the current, but not that much actually. About 6 times improvement in the current density. So it's really not there. And then we analyzed what's wrong with this generation. Then we took that learning to generation 3. So basically we have the self-aligned, then we have to scale. And then one of the major learning is that in the previous generation, when we were etching all the way up to TN. So what it was doing is that the plasma that we use for the etching, it is actually interacting with these holes and then getting reduced. We are getting much lower hole density because the plasma, it actually creates defects. And whenever you have defects, we reduce the hole density. It kind of annihilates the holes. So we take the kind of change the process, we change the etch process because it was we were using much higher power. So we change the etch process. We change the oxide that we were using. We did some ozone treatment around that. Yeah. So this is the interface that you can see GaN interface. And with that, we were able to get, you see, like 50 millimeter per millimeter. So we started with 1 millimeter per millimeter. Even 1 millimeter was a very good current density. So the first 1 millimeter paper was published in EDL because all the previous one was in the 0.001. So one was huge improvement. Now we are talking about 50 millimeter transistors. So long way we have come, like about 3 orders of magnitude. So this is the final device, but you see one of the problems is the on-off ratio is much lower, right? And also substitution swing is not that great as well. So 800 millivolts per decade, which is not good. So then we go from, so at that time I realized, okay, planar structure is not going to help us, I have to make a FinFET. So why do you make a FinFET? So you try to make a FinFET to increase the control of gate over the channel. So exactly the same reason people make silicon FinFET, I'm going to make gallium FinFET. So here is the process. So basically you form the source and the drain, and then you form the field, even though it sounds very simple. But the process development took me more than a year, because you have to catch 20 nanometer pins. It's not easy. It's a lot of sleepless nights in the field. So you etch the fins and you do other processing. I'm not going to the process details. Finally, you can see the source and the drain, and you have fins there. You see the connecting the source. These are like bridges between source and the drain. And then from the side, you can see the fin height is about 200 nanometer. And then you put the gate. So basically, this is the gate. So this is source, drain, these are the fins, and this origin is gate. So if you look from the side, you look at the cross section, you have the figures there. It was the last, I think it was the last publication during my PhD. Yeah, so now we look at the topics. So we have about 10^7 on the ratio. Now we are talking. And then if you look at the current density, it's 150. So it's almost there. We fabricated both E-mode and E-mode with the same process. So we have record low substitution swing, 85 millielectron per decade. It's still the record, I think. Both in terms of the on-off ratio, current density, and all that. So now let's see, let's benchmark our devices. So for benchmarking, we choose, there are different parameters, but we choose the two most important parameters, on current and on-off ratio. And we want on-off ratio to be as high as possible, on current to be as high as possible. So we basically want that part. So if you look at all the demonstrations, like all the red star is basically giving a ability. So look at, I think we still hold the record of having highest current density and highest on-off ratio. Now let's compare with the silicon, right? We're talking about power, so let's compare. So for a silicon 65 nanometer process, this is from TSMC. The current density is around 200, and we already have 150. Actually, right now we have data for it already shown 300%. It's almost there. So it didn't stop there. So after the FinFET, I started to look into the processes more carefully. Where could be more improvement? So one of the thing is that basically, if you look at the activation energy of magnesium, it's around 200. But what we have observed is that if you apply bias, and if you increase the electric field in the material, this activation energy actually goes down. That means by applying bias, you can activate more and more magnesium. And we have analyzed this physics, and we found out that the electric field has to be in the range of 110 kilovolt per centimeter. So basically, you have to make the device such that during the on state, your channel electric field is more than this. If it is more than this, that means you can have more failures. So that's one learning. Okay? And that's why when I make device, I always make very short-term device. Without short-term, you cannot have this kind of capacity. This is one of the understanding. Another thing is that when I was etching the GaN, we were using chlorine plasma. Okay? So what it does, it actually creates a shallow donor states, chlorine and oxygen, both of these. So when you have shallow donor states, it's actually converting this p-type to n-type. So that was actually reducing the holes. So what I did is that I developed an annealing process. So after the etching, after cleaning the sample, we do an annealing in nitrogen, and actually that solved the problem. And you can see that the sheet resistance goes down after the annealing. And with that, I made planar device again. So I started with planar device, made FinFETs, right? And then did the process development, and then started with the planar device again. Now let's look at the planar. It's a LG of 1.5 micrometer device, and we're getting 30 milliampere per millimeter current. You see, this is a long channel device. Still we're getting 30 because we improved the process. And we have seen that it has a clear scaling trend. As you are scaling the channel, reducing the channel, the current is increasing. And with 100 nanometer channel length, we got more than 100. This is a planar device, this is not a FinFET. So if we can do FinFET with this process, ideally you should get more current. Actually we did that, but that was after my PhD. This was my last paper. After my PhD, one guy did this, and he got around 500 million current, and we published it in IEEE. I was one of the authors. I already graduated, so I couldn't do that, but I had the road that you have to do this. So in summary, what we have developed is that we have developed a complementary platform where you can make both n-type and p-type. We have shown all the different circuit blocks that are necessary to use the system. And over the generation of 0 to 3, we have kept increasing the current. And right now we go there. So right now I'm going to talk about the group that I have at BUET. We start this group back in 2022. Right now I think I have about 10 members, 3 PhD students, masters, and undergrads, actually more than 10. So these are some of the works that my group did. I don't work alone. So there's a good part of being faculty. Okay, so right now I can just give orders to the students and they can go. So finally, after all of the hard work, 7 years of PhD, and now I have people to work with me. So this is the work that got published in TE. So basically, we developed a transistor where you can actually improve the linearity. So linearity is a complex problem for RF device. So basically, in all of your cell phones, mobile towers, everywhere, you need an RF transmitter. So if the device is not linear, then it will transmit unnecessary power. So basically, you lose efficiency. So it's a big problem for 5G. So in our 5G mobile PA, the efficiency is actually less than 10%, it's around 7%. So this work will focus on how we can improve the efficiency. This is the first publication from my group. And then we kept doing this work. So later on, we looked into the impact of Fermi level pinning on the same device. We presented it to EDTM and then got an invitation to write JES. It's almost accepted now. This is a collaboration with MIT. So we started to look into understanding the transport of holes in PA. All the processing was done there. We did the theoretical device physics work. It got published in JPL recently. So right now we have a lot of collaborations with a number of groups around the world. MIT, Stanford. We also get some funding for our work. And recently we have we started working on the AI accelerator. How you can power the AI accelerator with your IC. So yeah, that's about my group. Thank you. If you have any questions,
questions? First 1 month আপনাকে ডিভাইসটা একে করতে পারতেছিল না সামনে দা আউটপুট হলো কামিং কিভাবে রিজেক্ট কি
the first 1 month. First 1 month. First 1 year, more than a year. 1 month. So, আমি এখন বাংলায় সুইচ করি। সেটা হচ্ছে যে আসলে পিএইচডির একটা ফেজ থাকে ফ্রাস্ট্রেশন ফেজ, এবং এইটা যারা আসলে আই ডোন্ট নো মানে দিস ইজ আমার মনে হয় পিএইচডি করাটা এই কারণে ইম্পর্টেন্ট যে লাইফের এই ফেজগুলো দিয়ে যাওয়া, মানে যে কোনো রিসার্চের যে কি বলে যে ডিপ্রেশন একটা ফেজ আছে, যে কারণ হচ্ছে সামওয়ান ইজ পেইং, তাই না? মানে আসলে আমাদের পিএইচডি গুলো কি হয়, বেস্ট পিএইচডি গুলো হয় যেগুলো গ্র্যান্ট মানে কি যে কমনওয়েলথের যদি পিএইচডি হয় সেক্ষেত্রে কি হয় যে তোমার একটা ফান্ড আছে, গ্যারান্টিড একটা ফান্ড আছে। তো ইউএস এর পিএইচডি গুলো যেটা হয় ফান্ডটা আসে ইন্ডাস্ট্রি থেকে, তাই না? এখন ওদের তো কিছু টার্গেট সেট করা আছে, তোমার ফান্ডটা যখন প্রফেসর লিখছে সে তো কিছু মাইলস্টোন সেট করছে। এখন আমার যেটা হতো যে এভরি মান্থে ইন্টারের সাথে মিটিং থাকতো, এভরি মান্থে আমার ডেটা দেখা যেত। তো এখন মান্থের পর মান্থ যখন ডেটা ইজ নট কামিং, তখন ইটস অন নিউ। সো এইটা হচ্ছে খুবই সো ওকে, দ্য প্রবলেম ওয়াজ বেসিক্যালি যেটা আমি পরে রিয়েলাইজ করছি যে আমি তো তাকে একটা থিকনেস দিছি আর আমি তোমাকে একটা টিএম দেখাইছি, প্রত্যেকটা স্যাম্পল টিএম করা সম্ভব না। টিএম ইটসেলফ একটা খুবই চ্যালেঞ্জিং একটা কাজ। তো একটা টিএম করতেই তো মাস খানেক লেগে যায় একটা স্যাম্পল টিএম। তো যেটা হচ্ছিল যে আমি যে পি প্লাস জ্ঞান থিকনেস দিছি আর ও বানাইছে ওই থিকনেস আসলে একই, যার কারণে যখন আমি এচ করতেছিলাম I was etching the whole channel, or I was under etching. So appropriate etching also. Either there was no current or there was current but no modulation. Yes, এই কারণে মানে basically thickness was not right. How is the channel ছিল? This is the
I have one question in this case actually. 20 nanometer etching is very difficult. You know, as you said, why did you use chemical etching? Because compared to plasma etching, you said
actually
that you are
very
donors.
good question. So basically it was actually a combination of dry and wet. So basically what we did is that we are fin etch করতেছিলাম, initially fin etch করতে 100 nanometer, the dry etch করব 100 nanometer আমাদের কাছে fin আছে। এরপর এটাকে তো করতাম কি আমরা টিএমএইচ নামে একটা সলিউশন আছে, ওইটাকে হিট করতাম 70 ডিগ্রি সেলসিয়াসে, তারপর ওখানে রেখে দিতাম 10 মিনিট 10 মিনিট রাখার পর আবার চেক করতাম এই কতটুকু কমছে। আর ফিনগুলো অ্যালাইন দিতে হবে এ প্লেন বরাবর, গ্যালিওমেট্রিকের যে ক্রিস্টাল ওরিয়েন্টেশন এ প্লেন বরাবর একটা অ্যালাইন দিতে হবে। এ প্লেন যদি না হয় তাহলে আলাদা হবে। তো তারপরে দেখতাম যে প্রতি 10 মিনিটে কতটুকু গ্যাস হচ্ছে, ওইভাবে আস্তে আস্তে মানে 100 থেকে 100 ড্রাই এজ, এরপরে ওয়েটেজ করে করে রাখা 20 ডিগ্রি সেলসিয়াস। So it's a combination of dry and wet.
How is the dislocation density you have?
So for gallium silicon, dislocation density is about 9 to 10. So it's pretty high actually.
You didn't try on sapphire.
Sapphire টা আসলে
more
আমরা
costly.
sapphire টা ট্রাই করি না, কারণ হচ্ছে কি এটা ইন্ডাস্ট্রি বলে ওদের ইন্টারেস্ট নেই sapphire, কারণ আসলে
আমাদের টুইন স্কেল উপরে তো সাফারটা করে।
আর স্যাফারের আরো মানে জিনিসটা হচ্ছে কি যে আলটিমেটলি তো স্টোরি মানে স্টোরিটা কি মানে when you say gallium silicon but the story is big. If you can demonstrate in gallium silicon it has huge impact. আর সেটা হতে পেতাম, এক্স্যাক্টলি সেটা হতে পেতাম।
Industrial to second phase, you can tell that okay, since we have achieved on sapphire, why not go to
হ্যাঁ, এটা আসলে অনেকে করছে, কিন্তু somehow আমার প্রফেসর আসলে আমাদের এত প্রজেক্ট থাকে যে মানে ওই প্রজেক্টের বাইরে আমরা তো এখানে মানে বাংলাদেশে তো আমরা কাজ করেছি পেপার পাবলিশ করতে, ওখানে কিন্তু কাজ করতে কাজের জন্য পেপার বললে হইলো না হলে আই ডোন্ট কেয়ার, মানে আমার প্রফেসর কেয়ার দিচ্ছে ইফ ইউ ডোন্ট রাইট পেপার হি ডাজন্ট কেয়ার, কেউ ডিবিপি যে আমাদের গ্রুপে এমন আছে কিছু পেপার পাবলিশ না করে কারণ কি সে দেখে কাজ আপনার যে ফান্ডটাকে কন্টিনিউ করতে হবে, কারণ এই ফান্ড সাকসেসফুল হলে না সে আরেকটা ফান্ড পাবে। সো তার হচ্ছে বিজনেস হচ্ছে ফান্ড। এখন আমার দিক থেকে আমাকে চিন্তা করতে হবে যে আমি যদি এই কাজটা পাবলিশ না করি আমি 10 বছর পর ভুলে যাবো। Once you have written some paper, it's there, you can look at it.
Sapphire মানে আরেকটা খুব Sapphire is expensive, right?
Sapphire is expensive না, silicon carbide silicon carbide best, nano silicon carbide best কারণ হলো thermal conductivity silicon carbide much higher. So you know মানে সব RF application এ silicon carbide ইউজ হয়, ডিফেন্স অ্যাপ্লিকেশন। অনেকে তো জানে না যে আসলে যে আমাদের যে মিসাইল বা এয়ার ডিফেন্স সিস্টেম যেগুলো আছে আয়রন বোম বলে তো সব কিন্তু গ্যান ইউজ করে পিএ, কারণ এটার পাওয়ার ডেন্সিটি অনেক হাই। তো আমার যদি রেঞ্জ অনেক বড় কাভার করতে হয় পাওয়ার পাওয়ার ডেন্সিটিটাকে কাভার করতে গেলে গ্যান ইউজ করি। ইভেন মিসাইল যেগুলো হচ্ছে গাইডেড মিসাইল বলুন, ওই গাইডেড মিসাইলের মধ্যে গ্যান চিপ থাকে। কেন? কারণ এই মিসাইলগুলো কি হয় একবার এয়ার থেকে বের হয় আবার কিন্তু এয়ারের মধ্যে ঢুকে, যখন এটা বের হয়ে আবার যখন ঢুকে তখন এটাকে গাইড করতে হবে। তখন এখন এয়ারে এত ফ্রিকশন আর এটার টেম্পারেচার এত হাই থাকে, ওই টেম্পারেচারে আসলে সিলিকন কাজ করে না। তো এটাকে গাইড করার জন্য আসলে কন্ট্রোল করার জন্য হচ্ছে এই যে কারণে আমাদের কিছু প্রজেক্ট থাকতে হচ্ছে ডিফেন্সের সাথে বা এয়ার ওই এটা হচ্ছে MIT লিঙ্কন ল্যাব বলে একটা ল্যাব আছে, ওই স্পেশাল গ্যাং ফ্যাব আছে, ওইখানে আমরা আমেরিকান রাজনীতির সাথে
questions? In terms of mobility and other different parameters, can silicon carbide সাথে কিরকম compare?
সিলিকন কার্বাইডের সবচেয়ে বড় বেনিফিট হচ্ছে ডিফেক্ট ডেন্সিটি ইজ মাচ লোয়ার। ডিফেক্ট ডেন্সিটি এত লো, মানে সিলিকনে তো অলমোস্ট ডিফেক্ট নাই, অলমোস্ট নাই, মানে আছে না। সিলিকন কার্বাইডও খুবই কম, তো
Growth easier.
গ্রোথ ইজিয়ার, মানে ওই যে ইয়া মেথড, এই যে নর্মাল ওয়েফার মেথডে যেটা করে the downside of silicon is mobility is low, even n-type mobility is low, e-type তো almost non-existent। আর হচ্ছে mobility low হলে হয় কি you cannot switch at high frequency, তো হাই ফ্রিকোয়েন্সিতে সুইচ না করলে পাওয়ার ডিফারেন্স সলিউশনগুলো সব হচ্ছে বড় হবে বাতিল হবে। এই জন্য সিলিকন কার্বাইডের মার্কেটটা আসলে ভেরি হাই ভোল্টেজ না, মানে 1.7 কিলোভোল্টের উপরের মার্কেটটা হচ্ছে সিলিকন কার্বাইড। ওটা মোটামুটি ইন্ডাস্ট্রি কনসেনসাস যে ওই মার্কেট সিলিকন কার্বাইড, কারণ ডিফেক্ট ডেন্সিটি মাছ ওই ভোল্টেজে যেতে পারে, ওই ভোল্টেজে আপাতত নো ওয়ান ইজ টকিং অ্যাবাউট হাই ফ্রিকোয়েন্সি সুইচ, ইভেন দো দেয়ার আর সাম ডিস্টারবেন্স। অ্যাকচুয়ালি এটা কিন্তু ভালো একটা জিনিস, যেটা হচ্ছে যে একসময় তো আমাদের কম্পিউটার ছিল পুরো রুম জুড়ে, ইনিয়া কিন্তু পুরো রুম জুড়ে ছিল না, এখন আমার কম্পিউটার কম্পিউটারই হচ্ছে। আমরা যদি সাবস্টেশন যেগুলো দেখি, ঢাকা ইউনিভার্সিটি সাবস্টেশন বা যে কোনো জায়গায় সাবস্টেশন, বিশাল বিশাল সাবস্টেশন, ট্রান্সফর্মার তো বিশাল, কয়েক টন হচ্ছে একটা ট্রান্সফর্মার, কেন 50 হার্টজের সুইচ করতেছে। এটাকে যদি আমি হাই ফ্রিকোয়েন্সি নিতে পারি, এই ট্রান্সফর্মার কিন্তু ছোট হয়ে যাবে, তখন আমার অনেকটাই অ্যাকচুয়ালি there are some companies doing that, working with that, so তখন আসলে আমার হাই ফ্রিকোয়েন্সি ব্যাপার। সো ওইখানে উইন্ডোজে এখন কাজ করছে ফিউচারিস্টিক।
ম্যাগনেসিয়াম ডোপিং ডেন্সিটি কত?
আমার সাথে 390 এর মতো ছিল। সিলিকন ছিল around 70, 560
আমি ওদের বই একটা কোশ্চেন, ওরা আমার কোশ্চেনটা করে, মানে ইউ আর দ্য বেস্ট পারসন টু আনসার। এটা হচ্ছে যে অনেকেই জানতে চায় ইউ হ্যাভ বিন টু এমআইটি, মানে ওরা যদি দেখতে চায় হাউ ডু দে ক্র্যাক এমআইটি, what are your suggestions, experience?
আসলে চাচ্ছি পছন্দ না। তো অনেক আসলে যে আমরা যখন আমি নিজেও স্টুডেন্ট ছিলাম অনেক আসলে হচ্ছে তো যে অনেকে পরের বড় হয়ে আসছে পড়াশোনা করে কি হবে, তো আসলে এটা ট্রু না, একেবারে একটা রং। যারা এটা করে তারা তোমার হতেই চায়, ভালো চায়। সো আমি বলবো যে টপ স্কুলে যাওয়ার যদি তার মানে আমি একটা জিনিস বলি, টপ স্কুলে গেলেই যে তুমি লাইফে সাকসেসফুল হবে সেটা কিন্তু না। আমি কিন্তু জাস্ট এত কীভাবে টপ স্কুলে যেতে হবে, আমি জানি যে ওই পাথটা কী কী প্যারামিটার গুলো দেয়। সো ফার্স্ট থিং হচ্ছে তোমার যদি কোনো অলিম্পিয়াড মেডেল যদি থাকে তো বেস্ট, ম্যাথ অলিম্পিয়াড, ফিজিক্স অলিম্পিয়াড, বিভিন্ন অলিম্পিয়াড, অনেকে ইউনিভার্সিটিতে আসা থেকে করে থাকতে পারো, ওইটা খুবই ভালো, দ্যাটস এ প্লাস। আন্ডার গ্রাজুয়েটে সিজিপিএ ভালো আসলে কোনো বিকল্প নেই। মানে এই মানে টপ তিনটার যদি কথা বলি, ওরা আসলে মানে ওরা জানে যে সাউথ এশিয়ার এডুকেশন সিস্টেম এখানে ক্লাস টাইম বলে একটা ব্যাপার যে আছে ওরা জানে। সো এই ক্লাস টাইমটা খুবই ইম্পর্টেন্ট, খুবই ইম্পর্টেন্ট। অ্যাডিশনালি তোমার হচ্ছে রিসার্চ। এখন রিসার্চের ক্ষেত্রে আমি যেটা বলবো সেটা হচ্ছে যে এখন আসলে তোমরা আমাদের থেকে একটু লাকি এই কারণে যে এখন এখানে অনেক ভালো টিচাররা আছে। আমাদের সময় তো আমি রিসার্চ করছি তো মানে পেপার একটা ডাউনলোড করতাম, নিজে পড়তাম, নিজে বোঝার চেষ্টা করতাম, ঘুমাইতাম পেপারের উপরে, এরপরে নিজেই প্রবলেম বের করতাম, তারপর নিজেই এইটা হচ্ছে দ্যাট ওয়াজ আওয়ার রিসার্চ। মানে আই ওয়াজ লাকি যে আই গট ইট ইন মেবি। কিন্তু এখনকার স্টুডেন্ট যারা অ্যাপ্লাই করছে এদের প্রোফাইল, যেমন আমার একটা স্টুডেন্ট অ্যাপ্লাই করতেছে, তো মানে আমি আমার একটা ফ্রেন্ডকে ও সিএমএ ফ্যাকাল্টি ওকে পাঠিয়েছি, তো প্রোফাইল থেকে বুঝছে তো ওটা আমাকে সার্চ, কারণ তুমি আমি আমার পিএইচডিতে কি পাবলিশ করছি, আইডিএম করছি, ইডিএম করছি, এমএম করছি, ওর অনেক কিছু আছে। তাহলে এখন মানে ব্যাপারটা হচ্ছে তোমাদের পাবলিকেশন প্রোফাইল এখন অনেক ভালো হবে, কারণ বিকজ ইউ হ্যাভ গুড ফ্যাকাল্টিজ। সো ওইটা তো লাগবেই, অ্যাট দ্য সেম টাইম ক্লাস টাইম কিন্তু বিকল্প হয়ে আসবে। মানে আমি যদি এখানে এটা বলি ইটস কমপ্লিটলি। আর আমি বলবো কি, শুধু সিমুলেশন করে পেপার পড়া যাবে, তবে কিছুটা এক্সপেরিমেন্টাল কাজ এর আইডিয়া থাকাটা ভালো। সো ওইটা একটা ছোটখাটো এক্সপেরিমেন্ট থাকে, বিশেষ করে আমি কিন্তু বলতেছি ডিভাইস এই হচ্ছে সার্কিটগুলো আবার বন্ধ করতে।
স্যার এক্সপেরিমেন্টালি যে ডিভাইসের কথা বলেন ওটা হচ্ছে আমাদের দেশে আসলে
না, এক্সপেরিমেন্টাল ডিভাইসের কথা বলি, এক্সপেরিমেন্টাল কাজ। ফর এক্সাম্পল আমাদের তো ক্লিন রুম নাই, যেহেতু আমরা ক্লিন রুম বাড়িতে পড়বো, তো আমরা রিসেন্টলি একটা প্রজেক্ট করতেছি, আমার একটা মাস্টার সিস্টেমের পরে সেটা হচ্ছে আমরা একটা প্লাজমা মানে মাইক্রোওয়েভ বাসা মাইক্রোওয়েভ, ওইটা দিয়ে আমরা একটা প্লাজমা ওয়েভ গাইড বানায় ওইটা দিয়ে একটা এচ করার চেষ্টা করতেছি, বা প্লাজমা জেনারেট করে সেখানে সিলিকন ন্যানো পার্টিকেল বানানোর চেষ্টা করতেছি। তো এটা হয়তো খুব ভালো জায়গায় পাবলিশ হবে না, কিন্তু ইউ হ্যাভ দ্য এক্সপেরিমেন্টাল এক্সপেরিমেন্ট সো দ্যাট ইউ ক্যান সেল। সো তোমার পাবলিকেশন হবে হচ্ছে ওই যে সিমুলেশন বা মডেলিং বা ওই কাজ, কিন্তু এক্সপেরিমেন্টাল তুমি দেখালে যে আই হ্যাভ দ্য এক্সপিরিয়েন্স। কারণ অনেক প্রফেসর চিন্তা করে যে আসলে কিন্তু যেহেতু কোনো এক্সপেরিমেন্ট আদৌ তুমি এক্সপেরিমেন্ট পছন্দ করবে, কারণ এটা কিন্তু একটু ডিফিকাল্ট। যেমন আমার মনে আছে আমি ক্লিন রুমে যখন যেতাম, আমার ক্লিন রুমে থাকতেই পারতাম না, কারণ হচ্ছে গাউন ডাউন করার পরে যখন গ্লাসটা পরে ফগিং মানে নাক থেকে বের হয়ে ফগিং, এটা একটা মানে অ্যাকাস্টম হওয়ার একটা ব্যাপার আছে। তো আমি 3 মাস কোনো কাজ না করে জাস্ট গাউন করে সকালে যেতাম, বিকেলে বের হতাম নিজেকে ট্রেন করার জন্য। তো তখন দেখছি গাউনিং ওয়াজ ইজি। তো এই ব্যাপারগুলো না আসলে প্রফেসররা চিন্তা করে যে লাইক করবো কিনা, এগুলো তো একটু রিস্ক। তো ওইটা হচ্ছে একটা experiment. It doesn't have to be like device, but যে কোনো ধরনের একটা এক্সপেরিমেন্ট Any other questions?
Okay. Any questions?
Thank you.
Let's
Thank
thank
you
the
for
speaker.
coming.